so far. So I'll try to find a way to solve it. Okay, so last lecture we talked about different stochastic gradient descent optimizers. We talked about a bunch of those. Also, I checked the formulas. Those formulas were correct. So whatever you had was correct. I was talking about ADA-grad, RMS prop, Adam, and momentum-based gradient-based stochastic gradient descent. So in this specific example, we saw that Adam could outperform the others by converging faster to a local minima, right? So it has this was, as I mentioned, was a sort of a loss function. So the loss function was minimized sooner. So what we call it is like the convergence is faster. Convergence rate is faster, so it converges faster. All right, and then finally we talk about starting with a binary logistic regression we had previously. We moved toward a multi-class logistic regression. So in a case of, as a recap, on a case of binary logistic regression, you have your weights coming here. So W0 for the artificial superficial coordinate that we added as x0 equal to 1, right? And then your W is corresponding to each x, so W1 with x1, W2 with x2, up to WD, which was your feature size, to your XD, right? And we would just compute the output signal and then apply a function of theta. We call it in logistic regression we use sigmoid, right? So that was the vanilla case of logistic regression in a binary case. We also mentioned that, yeah, so that was the sigmoid function, and the output was sort of a probability, an estimate of the probability P of your W's, where it would give y equal to 1 for the case of input x. Also, I recalled another thing that was of question. The other, let me just find it out. Perhaps it's better to find it from the previous slide to showcase it here. 9. So this shape that I was presenting you the last lecture, and I was receiving questions about it, is just like your gradient of En, right, for your omega k parameters. On the case that we apply, we compute the gradient matrix with respect to the WLs. That's why we put the WLs as an underset. It's like you are having this function, so f of x is ax squared plus b, right? And then we compute the gradients with respect to x, and we treat the x as variable. So the output would be 2ax, and this is constant, would be gone, right? So I could just write it x here as an underset. If I was treating my a as variable, right, this would have gone. So the output of this, given a as variable, it would be x2, right? Because a would have been gone by and replaced by constant. So that was why you have this pointwise error of your omega k, and we are computing the gradient based on treating the variable as w. So that was the case. Hope that clears the questions. Right. Let's go back here. Okay, so that was the binary logistic regression. We talked about softmax in the previous lecture. We call it softmax regression or multinomial regression. So on a case that you have multiple classes, we needed something in between your output signal and the final output that sort of normalizes based on the number of classes, right? And the output we talked about that one of them would be the correct output. For instance, say that was the correct one, and these two were incorrect, right? And we talked about normally it has a higher probability. So if you want to show it this way, for the case of multi-class logistic regression, so what we have here is, again, your weights and your variables, so your x's up to xd and wd, right? And then for each of them, you're going to have one s up to the class of c, so s1 up to sc, and then the rest of the thing will be taken care of by the Softmax classification. So it's going to output your estimate P1 up to the case of PC, right? So for each of them. And then we would compute that e to the raise of Si for the class of correct one, for all the classes actually. So for each of those classes, we would have normalized the output of the S divided by the sum of all of those, right? We talked about, for instance, if this would become 120, 40, and 5, that would be 120 divided by 120, 4, 5. For the first one, the second one would be 40, 120, 4, 5. And the rest, the third one would be 5 divided by 120, 4, 5, right? And we would have just picked the higher one because it would normalize it and you had some probability from 0 to 1, right, as the output. Say like this would have become like, I don't know, 81, and this would have become, I don't know, 17%. So that was the job of your Softmax here in the case of multi-class, right? All right. As another recap, you already know if you expand that S in the signal S of I here, right? In the case of logistic regression, would be that value WT xn, right? And you have C classes, and we talked about the point that it's going to generalize the logistic regression to multi-class. So basically, you've known all of this. Now let's talk about an interesting topic that uses all of the things that we've already been discussing so far, and it's going to be neural networks. So in the late 50s and 60s, so because perceptron was introduced in the late 50s, right? People have thought about using multiple perceptron, right, and to stack them up and to represent more complex features. Because a perceptron was only able to classify, right, your binary cases. What if you're dealing with a nonlinear data? What if you are representing a much more complex situation where your data is not linearly separable, or you need some accuracy that you can't achieve with just one perceptron, right? So later on, the idea of a multi-layer perceptron, or what is known as MLP, emerged, and is just as easy as it can be read. It consists of at least 3 layers, 3 perceptron nodes. Each of those are perceptron. One input, some hidden layers, so that's why I put the S in the parentheses. You could have at least one hidden layer or many hidden layers, and of course one output. So you have for sure one input, one output, and certain hidden layers. So we want to stack them up to be able to represent and classify more complex data, right? The only difference is in MLP, those nonlinear, those hidden layers, instead of having a linear function, which we call it an activation function, we talked about it. We will talk about it today in detail. Instead of having a linear function to activate the output of the hidden layers, they're having nonlinear activation function. Any function that is nonlinear. So that's the general definition of an MLP. But for now, in the next upcoming slides, we're going to use sort of a stack of multiple perceptron still with a linear activation. And then we move towards having a nonlinear activation. All right? So, as an example, just look on the top left side, right? Well, actually, let's start from the top right side here. So we have one hypothesis line, we call it H2, right? It is able to classify this region, right? Pluses and minuses. The data is linearly separable. We can easily separate this data with just one perceptron. We call it H2, right? We have two features, thus two x's and one hypothesis line, okay? Looking on the middle one on top, there is also another linearly separable data, but in the reverse order. So this will classify the pluses, this will classify the pluses here, and minuses there. So we call this a second hypothesis. We call it H1, right? Now we have H1 and H2. So if we were to classify a data set which is non-linearly separable, such as the one you see here, right? You have pluses, minuses, and pluses, right? There's no way I can separate this data when I have two x's with only a single line. If I do this one, I have incorrect classification. If I have this one, incorrect. Split in half in either way. There's no way, because it's not the linearly separable, right, data. However, simply by just adding both of the hypotheses we had on the upper middle and upper right and stack them together, so that was my H1 and this is my H2, right? Easily I can separate this now, because H1, remember, it was supposed to classify minuses here and pluses there, so this side, and H2 was supposed to classify pluses and minuses there, right? However, none of them alone can do such job, right? So I have to find a way to combine these two, right? To combine the effect of these two and come up with some logical operations to use these two to come up with this output, right? So say if I combine my, okay, let's just stay here. We don't want to go further than that. Let's just have, again, one perceptron, one of these two cases, okay? Simply by just playing around with the weights, okay, I can generate an output that resembles an OR function or an AND function. Let's see how. So that's my x0, right, which is 1. That's the weight of x0, W0. This is W1 and this is W2, right? W1, W2, okay? So you see, by adjusting my W0, which, as you know, that was a bias term, and inputting both 1 here, if I input both 1, because this would be 1 multiply 1, and this would be also 1 multiply 1. In order to have an OR in the output, right, I need to adjust the weights to the point that the output resembles an OR function. Because remember, an OR, That's your output, that's your input. So x1, x2, right? This could be 0 or 1, could be 0 or 1. If both of them are 0, the output would be 0. If either of them is 1, so you're going to have 1 there, and have 1 there, and then the 0 still would be 0, right? Well, actually, I represent it in a very bad shape. The worst that I could. So, remember for the OR, I have 0, 1, 1, okay? And then the output, I can have only 0 when both of them are 0. And if either is 1, I don't need even actually this. If either is 1, the output is 1. If both are 1, the output is 1 again, right? So you see, by simply adjusting this to 1.1, I can represent, with using one hypothesis, one perceptron, I can represent an OR function. Does that make sense? Why I have that 1.5 over there? Remember, this is a perceptron, right? Output either 0 or 1. Okay? You cannot now play around with all those 4 combinations, right? Say this one is 0, this one is also 0. So 0 and 0, so the output would be 0 again, right? If either of these are 1, I'm going to surpass to the point that I always have 1 in the output. So that's an OR function. Does that make sense? Who didn't understand? Yeah. Can anyone explain? So I'll make sure you got it.
Is it because to activate it needs to like reach a certain value?
That's right. So
you have the 1.5, and then if you have at least 1 from either one of the other ones, then it'll be activated. But if you don't have either of them, then it's at 1.5, which is evaluating to 0 still.
Right? Does that make sense? Yeah. So think about this as a linear activation, right? It's either 0 or 1. So those signals who are coming to this area will all be slashed to 0, right? Or let's say -1 and +1. Think about it this way; it would make much more sense. If you pass that threshold, whatever you have above is going to be 1, right? So by applying this threshold to 1.1, 1.5, you're going to pass that threshold, and you'll be 1 in the output no matter what. I guess there are still doubts there.
Professor, so
let me just clear what I've messed here so you can see it better. Yeah.
Okay, so you the W0 always has to be 1.5.
It's just we adjust the W0 manually, right? To mimic the function of OR using one perceptron, right?
Oh.
I don't really understand the relationship between the diagram at the bottom and the top. How are they related?
Like this top?
Yeah.
Okay. Yeah, I mean, this is just stacking these two up to represent such shape which is nonlinear, right? But I ask you just to step back, just forget about this for now. Let's just talk when we have only one perceptron, okay? How are we going to be able to, let's forget about the top side here. How are we going to be able to make an OR or AND with only one perceptron, right? We have two features, one X0, one W0, W1, W2. So we are playing around manually and find a weights such a way that we can represent an AND or an OR, okay? And this is your perceptron. Remember, it was outputting this or this, right? So call it one class, minus class. This one call it plus class, okay? or minus 1 plus 1. Okay? So whatever that is in the negative side, it's going to be a slash to minus 1. Whatever that is above positive side is going to be a slash to positive, right? Output. Okay? So, having this in mind, can anyone explain why this always outputs, why this can output or? Because remember here you can input either plus 1 or minus 1 also. As an input you can input minus 1 or plus 1, right? This is your input, right? You can feed it minus 1 or plus 1. It's like you're having one line, you're feeding it data. So you set your line here, I'm feeding plus 1 and minus 1. Is it recognizing it correctly or not? Is it clear? Can anyone explain what's it about the case of AND? Why we are using minus 1.5?
So essentially, if you are, but you're setting your bias lower, so that if you only have one input, you won't pass that threshold. You get both, then you'll.
Yeah, exactly. So if I have one of them 1, I'm gonna add 1 plus minus 1.5. I'm still will be in the minus domain, because if one of them is 1, I have to add this plus this. I'm still in minus, right? And this will slash me to the minus, so it will be 0. So or minus 1, one of the classes, right? Unless I have both of them on, I'm not gonna be able to just pass this here towards a positive and goes towards 1. Does that make sense now? I'll stay here for like 30 seconds. Yeah, so you can have a look at it. Let me just get rid of this again.
So the inputs are not 1 and 0.
I mean, you can feed them an input, which is binary in this case. So either plus or minus. So say you have a model, you are feeding it data, right? So you have set this line. This is you have learned this line, right? By learning this line, I'm talking about learning the weights, right? You have learned the weight of this line. Forget about the data. Now you have a line. You have a learned model, right? In the case of binary and twos, you have just a line, okay? And then you're feeding it data. So like you put plus or minus, okay? Is it able to correctly classify it? And if yes, what's the output? What output function it resembles? Is there a question over there? Is there a question?
I think in the OR part, aren't we supposed to take, instead of 1.5, aren't we supposed to take minus 0.5?
For OR?
For OR. And is fine, I got the AND part, but in the OR part we have a problem. So,
So let's simulate your case. If it's minus 1.5, okay?
Yeah.
Let's try both cases. So I'm gonna feed minus 1 and minus 1 here, or
it should be minus 0.5, not minus 1. 0.5.
0.5. So let's have 0.5. And remember, in many cases there is not a single valid question, because in the case of a binary you might have just this line, this line, this line up to this, right? But let's simulate your proposal. Okay, minus 0.5. Okay. If I pass them both the 0 case, so 0 here is minus 1, like, because we have either plus 1 or minus 1.
Okay,
Yeah, I mean, just don't get confused, because okay, in a logical case you would have 0 and 1, right? In this case we have minus 1 plus 1. It's just two classes, just blue and red. Yeah, just It's a logical, it's a binary choice. Or perhaps that was the reason, right? So treat it as -1 and +1 in this case. Okay? This could have been even higher a little bit. The result would be the same. Okay? So far. Now, so we used one perceptron to represent an or an and by just tweaking a little bit with the weights, right? These weights. Now let's see how we're going to tweak to represent this type of classification, a nonlinear data. Okay? Now, I'm trying to stack them up to represent this. All right? So remember, this is my first perceptron, hypothesis 1. This is my second perceptron, hypothesis 2, and that bar on top represents the negation case, right? So whatever it was producing on top, plus and minus, the negation makes it the other way around, right? So this is minus, and this is pluses, right? It's a negation, it's a logical operation on that. Just like this, for the case of H1 and H2, I can use a negation of H1 multiply H2, right? And if I treat it like this, you see these two together, trying to write here. Yeah. So this can represent my XOR. Just don't call it anything. This can represent what you saw in the previous figure, okay? How are we gonna represent such H1 negation H2 or negation H1 H2 with another layer, right? So my leftmost side of the network, we can call it now, starts from the inputs, right? And uses the one of the hypotheses, one of the perceptron. My second side is using the output of these two, right? Here it uses the output of these two. When I'm saying H1 negation H2 is when the weight of H1 outputs 1 and the weight of H2 outputs the other class, -1. I'm talking about these two now. Let me just get rid of this. So when this one is 1, when this one is -1, again, messed it up. So blue is for H1, right? On the case of positive, and red is always the case of negative. So when I'm representing H1, H2, it's like I'm treating the case that this one is H1, and I'm treating the case that H2 was -1, right? Here, if I treat these two, I'm going to have H1 negation H2. If I want to generate the other case, I have to treat it as the other way around, +1 and -1 here, and the other case would be +1. So you see, when we have multiple input, they can generate multiple output because these are connected on the next layer. So this one is connected towards both of the next set of layers. Yep. Yeah. Actually, I have a better example after this. This would makes much more sense now. To go further, perhaps. But your question was, you want to see what? -1?
Because you're putting in 1 and -1. So you wouldn't pass the threshold.
So on this level, right? So this is my first level. That's my second layer, which is a hidden layer, we can call it, or second layer, and that's my output. Okay. On the first layer, I'm using one perceptron with each of the nodes, right? So it was as if that these are my x's, x0, x1, and x2, right? These are connected to this as well. That would be my input. Okay. On this layer, my hidden layer, I'm having the output of both of my perceptron is like I'm stacking them up, right? To use both of the outputs. I have 2, so I can generate 4, including the bias term that comes here again. I can generate a variety of outputs here. So using this, when I stack these 2 up, I can generate H1, negation H2, or negation H1 and H2 at this layer, right? Because I'm adding one more layer, I'm making it deeper, right? If you just omit, if you don't look at the hidden one, that would be just this one layer, right? So what this module is able to output is only maximum either or and, because it's a perceptron, it's a linear classifier, and it's only one. So if I want to represent such a nonlinear data set, I'm not able to do so, right? With only one. But if I add them up together, so 1 and 1, and tweak around with the weights, I'm able to represent a more complex class, right? So the first layer uses either of those, a perceptron, and the second one uses the output of those, right? H1, H2. So now I'm going to play with those. I can negate the first one and the second one and play around with the weights as well to represent a more complex function here. Okay? And in reality, what you do, so just like I mentioned, that would be your input with the x's. These are your weights. So you multiply them just like what you knew before from the linear classification and then so on, regression and logistic regression. This is your output, and this is your hidden layer. So in reality, we call this a 3 layers feed-forward network. We call it feed-forward because we are feeding it from the left to right. So in neural net, left to right is feed-forward. If you come from output and go backward, we call it backward, of course. Is it clear up to now? These ones are also, each layer has its own x0, right? On the first layer, we call it x0. So these are also the bias for each of those layers. Because the more we stack up more layers, each of them can have their own bias. Yep. Go.
I was just wondering, isn't the and or the or still technically a nonlinear classification? This is the combination of those two hypotheses.
I mean, and or can be represented with just one perceptron, just like we saw here.
Yeah. But isn't that still like a nonlinear classification?
Why a nonlinear?
Because like you're saying that it has to be both, it has to satisfy both the H1 and H2. Is that what the and is?
No. It has to satisfy only. No, I was talking about different inputs. Don't mess inputs
Oh, okay.
with the weights. So these are your inputs, right?
Yeah, okay.
These are your weights
Yeah.
at x and w, right?
Oh, so it's still
Right.
okay.
So up to here is using one perceptron, right? But up to here is the output of the first and the second one, right? So you have both of them here. Now, how are you going to play around with those? You have, again, 2 more options. This could be negated, or this could be negated, right? Because in one of the cases, this is -1, and the other case, this could be -1, right? So -1 is like here, h1, negated h2. This one is -1 comes here, so h1 is negated, and positive h1 comes there, right? It's just logical. Yeah. Yeah.
So, oh,
You were before Francis. Yeah.
Yeah, I just don't really follow. So like, you're negative. So if you're looking at the first
Here,
division layer,
here,
the one to the left.
here.
Yeah. So you have -1, 1, and -1.5. So like, what is that? What are you calculating? What do you? I don't get what's going on.
So this portion is your AND portion, is your OR portion, because it was minus, yeah. That was AND portion. Just look at this one, x1, x2, and this, okay, with the minus 1.5. This represents this.
Yeah. So can you just explain that?
So here, how was it? E. Can't remember calling this. E. So, in order to generate an AND function, so remember AND is when both of the inputs uh, 0, 0, 1, 1. Okay, so these are
0, 0, 0.
and 0, yeah, 0, 0, 0, 0. So we have 2 inputs, right? We can have 4 combination of inputs. The first input 1, the second one 1. Every time I represent it in reverse. This could be what? -1 plus 1. This could be -1 plus 1. In total, we have 4 combination, right? So try out with these weights and let me know what's the output.
So those are your inputs. The one.
Yeah, so these are inputs. Those inputs are like your data, right? Okay, so the data could be, and remember this goes there, right? So think about it as blue and red, 2 classes, class 1 and class 2. But in this case, we are representing it with -1 and +1. Okay, if this one has -1, and this one also has -1, you combine these two. This is the x, this is the weight, right? The multiplication comes here, -1. The multiplication comes here, -1. And this one is again -1.5, right? You sum them up, and then you add the perceptron on the output, right? This is an activation for the output. Anything before 0, which is on the minus side, will be a slash to -1, and anything above will be a slash to +1, right? So the output of this was what? -1, -1, -1.5, -3.5. It was here, right? It would slash it as the output as -1. So having an input of -1 and -1 will give you again -1. Having an input of, so the only case it would pass to +1 was that both of them are positive.
What if it's 0? What if you
We don't have any 0 here. The classes are -1 and +1.
No, I mean, like, say your threshold was negative, the bias -1.5, so that was -2, and both your inputs were 1. You have 2 minus 2, which would be 0.
Yeah.
What would that be?
Which would be still -1. The output. Anything in the minus side,
Okay.
up to infinity, will slash to -1, right? So now thinking about this -1 and 1 as 0 and 1, so 2 classes. But anyway, this mimics an AND function for 2 classes. Yeah. Is that clear for everyone? Ask questions if you didn't get it. Because this could be one of the easiest questions in your exam, right? And you can just easily answer it. It's pretty easy. All right. Any questions?
And then this whole thing can be either and or working depending on how we tweak the weight.
Yeah. So up to here the output could be AND gate. The output of this could be OR gate. But again, we go one step further. We stack these to AND and OR, and the output is virtual and XOR here, which is sort of a nonlinear classification for a nonlinear data such as that. We'll go towards that again.
But I guess what I'm asking is depending on how you adjust your weights, that'll
Exactly.
help the
Yeah.
function.
So that's right. And you see, simply by stacking up simply by stacking two simple perceptron, we can represent many different outputs. And actually, next week you're gonna see that in 2 weeks, somebody in the 60s provided a proof in math that got well known after that as a universal approximation theorem. And basically, he was saying that with neural network, we can represent any structures by just stacking them up. And you see how powerful. Then that's why they are very powerful. Because remember here, this is another example of having a nonlinear separable data set, right? Here there are pluses and there are minuses outside. There's no way I can represent it with anything, right? That's my target app. I'm trying to introduce some form of stacking multilayer perceptrons to represent such a target data, okay? So if I add 8 perceptron, which is like 4 lines, 1, 2, 3, 4, and 1, 2, 3, 4, right? I'm able to represent this data. What if I add 16 perceptron, right? It's as if I'm able to represent even these areas, all those nested combination of those, right? So adding more perceptron is like stacking them up and making them deeper and deeper and deeper, okay? So you see that by just this very small notion, how powerful they can get and how easily they can just make themselves computationally intensive, because you have to compute so many things now on the right end. So after this example, let's just talk about them in more formal way. So let's define neural networks. In a simple case, we can define neural networks by a two-layer network and a binary classification, just like what we saw there. So this is your input layer. Well, actually I have it. This is your input layer. Each of those have their own weight, so they can be connected to the next layer. We call this hidden layer. You can have many hidden layers, right? And then this is your output. Within this paradigm, we have a theta here, and we have a phi there. We call this a nonlinear functions. Later on, you see that we call this an activation function, because they can activate the output based on what you feed them as input, right? You remember the sigmoid in, or even perceptron, right? This is your input. We can feed it anything. So minus infinity. Or some classes, in a case of binary, you can just feed it minus and minus, right? In a case of multiple classes, you can just feed them anything, and the output would be either +1 or -1, right? It activates the output in a way that the output is only +1 or -1, right? No matter what you input it. So we call it a linear activation. Remember, for the linear regression, that would be like this, right? it was the real values. So whatever you were inputting, it was the output. That was another linear activation. In the case of logistic regression, you remember it was a sigmoid function, right? Whatever you were inputting here, the output would be somewhere around 0 to 1. And we talked about the probability and the log loss and the cross entropy because of being from 0 to 1, right? In the case of neural network or multiple layer perceptron, we use normally another activation. We call it hyperbolic tangent. And this is sort of similar to what we had with sigmoid, but instead of 0 to 1, it's minus 1 to 1. So whatever you input, again, you're going to have something in the output in the range of minus 1 to plus 1, but it's in a real range. That's the range of minus 1. We'll talk about it later. But these are actually representing those. So this theta, you've already known it. You've already been taught at logistic regression. That was your sigmoid function. And this phi could be another that we will talk about it today. Okay? So basically they are activating the output in a way that they are functioning themselves. That's why we call it an activation function. They could be linear or nonlinear. Alright, so let's talk about some definition here. We call W, I, and J the weight on input vector I, that's why it's preceding the J, to hidden vector of J. It's those weights that you pass from input I to the output J. And output J could be a hidden layer one step further, right, on the right side. So we represent it this way, Wij. All right. So if we want, using this notion, if you want to present, or if you want to represent the H's here, the perceptron, the hypothesis we have, right? How are we going to represent them? Using the weights Wi and J. H of J, either of those output of your activations, which is the output of actually your hypothesis, it's, yeah, before this B, it's me. So this is the output of this activation, right? In this case, it's a theta function, right? So whatever you input, it's going to output it because it's a function, right? It's going to activate it in a way that it works. Such as, I don't know, if you think about an f of x, it's a function that activates the x because you input it x, it's going to output something, right? Just like this one gets as input this value and it's going to output, right? So as an input, it gets what? A Wi and J plus the sigma I1 up to d Wij xi. So that was the first bias term. And when we simplified it, just like what we had before, it was this way, right? We knew it already. Is it clear up to now? All right. So now we started from this, where it represents those Wi and J, all these lines crossed. And then we are here, we can represent. So now if we stay there and look back, see how did we end up being here? It's like we have to take into account whatever that was behind this guy, right? Whatever that was behind this guy and whatever it was behind this guy as well. We represent it on a second line. Now let's go one step further. Let's stay here and see how did we arrive there. Okay? Now, looking from here towards Pat, here we have another activation function of the previous layer with a V0, which was the bias term for that specific layer here, right? That was here. I have those V1, V2, and V3 or Vn, I mean, could be anything. Like this could be more lines. So the summation of j's from I to n, Vj hi, and that's the bias term for that specific layer. And you can basically simplify it. So instead of this value, you can use the same value you found in the previous layer, right? The summation of Vj's hi, hi is this. You found it there, right? So you have Vj and this. So in neural net, we use a phi, which is another activation function than theta. We call it hyperbolic tangent. We will talk about it today. Okay, is it clear? It's just basically expanding it to whatever we had from the previous layers, right? Because we are feeding forward the output of the previous layer, right? So if you stay at the last layer, the final layer, and look back, that's how you arrive there. The output is corresponding to the activation function of the previous layer, which was corresponding to the activation function of the previous layer, and which was the output of the first input layer.
So are we just using the different V or nu or whatever for the output layers weights?
Yeah, like just as we mentioned here. So here, this is V, this is the edge. Yeah.
But it's just the. I'm just wondering why we are using a different notation.
Because this could be an infinite number of layers in between. Yeah, this could be many hidden layers. Yeah. In this case, it's only one, so it doesn't make sense. But say this was multiple layers, right?
What is the X underscore?
X is input.
The next line X underscore first lines. X underbar.
X high?
X underbar here.
Here.
Yeah, X underbar.
That's the vector of input. That's the vector of input because this is the vector. Yeah. Oh, I guess I described the issue. Perhaps you guys asked the previous lecture. So you remember you asked me about what was that? I forgot. The gradient. The gradient En with respect to W's. So it's just with respect to W's. You remember? Yeah, that wasn't a typo. It was okay. So as if we treat those W's as variables. All right, let's go back here. So now we can represent the output as an activation function of the bias term for the previous layer, which was the hidden one, and the summation of all weights multiplied to the input, which was the output of the previous layers as well. Okay. Now let's see what type of activation this phi is here. So we call this just like what we called before the sigmoid. This was the sigmoid, right? We call this in general an activation function, right? Phi or whatever we can call it. The common choice for neural network is hyperbolic tangent, so tan h, and this is the function symbol, which is equal to e to the raise of s minus e to the raise of minus s divided by es plus e minus s in the denominator. Let's see how does it look. So it spans in x from minus infinity to plus infinity, but the output, the y on the vertical axis, is limiting towards +1 on the positive domain, and it's going to limit towards -1 in the negative domain, right? And this is what is called a hyperbolic tangent. This has more positive advantages with respect to a sigmoid that we were using in logistic regression. First of all, it's going to output from -1 to +1. So that's the first advantage. On the case of logistic regression, it was interesting for us because it was outputting from 0 to 1, so we could have played with the likelihood, right? Because it's sort of a probability after all. But here, the positive advantage is the gradients are in general higher than a gradient of a sigmoid function, which was from 0 to 1. So normally, research has shown that the models that are used with hyperbolic tangent as an activation function, they can converge faster. We'll talk about all of those details later. Okay. Again, another advantage is zero-centered. The center is 0, whereas in the case of the sigmoid, the center was half, right? Here it was crossing half for sigmoid, and here it is 1. But hyperbolic tangent is zero-centered, and on both extreme ends, right? S is the saturation point would be around -1 and +1, right? Okay. Another advantage for having a hyperbolic tangent is in neural network, because of a stochastic gradient descent and doing the minimization problem, and also another approach that we will be discussing it in 2 lectures, which is the back propagation or feed. Instead of going feed forward, we're going to go backward. This is called a back prop. We need to compute many the derivation of activation function, right? So another feature for hyperbolic tangent is the derivation of theta prime of s is simply 1 minus theta square of s, which makes the computation very easy if you want to run it in a huge graph multiple times, right? And it has a very simple proof. So it's a hyperbolic tangent. So if you want to make a derivation with respect to x, so d hyperbolic tangent s divided by dx is going to be tangent, as you know, is sine divided by cosine. And then if you expand it and make the derivation, and you're going to come back again to this value, which itself is 1 minus hyperbolic tangent square x. So your theta prime of s is 1 minus theta square of s. Okay? So that makes it very easy for us to compute all those derivations that we need to compute later on. All good? All right. Just like what I mentioned there, these are the differences between your sigmoid and hyperbolic tangent. So in general, this is going to output -1 to +1. The sigmoid will output 0 to 1. On the case of hyperbolic tangent, we have larger derivatives near 0, right? Because the slope is higher. And thus, research has shown, the experimental result has shown that better stochastic gradient and convergence is going to be helpful to converge faster when you use this activation inside your neural network. All right, so let's see an example here. Now we have, suppose we have two hypotheses, two perceptron lines, H1 and H2, right? So the first one, the line 1, we call it H1. On this side is going to classify pluses. On the other side is going to classify the other class minus ones, right? And the hitting, where they hit X is +1, X1. Where it crosses X2 is +1. So the line is virtually X1 plus X2 equal to 1, right? Say we have a second perceptron, the second hypothesis, that does the classification this way. On the upper side, the pluses, on the lower side, the minuses. So where they cross X1 and X2 are +2 and -2. So it's virtually, the linear line is X1 minus X2 equal to 2. Okay? So now we use these two lines, and we are interested in forming this. Right? If we want to make an OR of H1, H2, right? If we stack them up as the following, the first line, which was going +1 and -1 there, and a second one, which goes +1 and -1 over there, we can combine it just like what we saw before. We can represent output OR this way and AND this way. So if we play around with the weights, we can actually classify such data sets easily with these two. Okay? This is we saw already. Now let's have a question in general. What if instead of a linear activation function, we had a neural network, right, that has the same structure, but instead of a nonlinear, we had a linear activation function. So instead of a sigmoid, we had another thing. Instead of hyperbolic tangent, we had a linear, right? So say your hypothesis J, which was the output of your first layer, your hidden layer, right? And the output, what if this one would be a linear activation function instead of sigmoid, or instead of hyperbolic tangent, right? This would have become a linear function in X, right? What would be the output structure? What do you think?
Should be directly proportional to X.
What was that?
Directly proportional to X, right?
Yes. Not completely directly, because we had the first layer with its own sigmoid, right? So what would have been the output? Let's call it the new W's as WEFF. So the output was this. The output of the hidden layer, Vj multiplied Wj, right? Without an activation function, because we don't activate it non-linearly. This is a linear activation. Still, your first layer had its own sigmoid, right? You simply see that this would have become a logistic regression, right? Yeah, use him last here. Does that make sense?
What happened to the transpose?
So all the transposes are just a vector notation of the same sum, right? I can represent it either this way, for this, so the sum I1 to n of my x and w, wx could be w transpose x in vector, right? Because this is like a pointwise, this is my w and this is my x. The output is actually pointwise multiplication and sum them up. It's actually a sum, right? These are different notion. Notation wise, it's a vector notation. The other one is like in algebra, right? All right. So in a high-level manner, activation functions are very important in neural network, right? We have a two-step process. Say we apply nonlinear transformation. That's my hypothesis, or the one that was the output of the first layer, which is the hidden layer, right? And afterward, it's as if we are applying a logistic regression to the output of this, right? It's a two-step logistic regression with a nonlinear activation, right? Can you distinguish the differences between a logistic regression and a neural net? With a nonlinear activation, yeah, exactly. But then in a simpler case, it is a multi-layer perceptron with a nonlinear activation, right? But you could stack those up as well. All right, so let's have another question. Hopefully we come up with the answer for this. What would you think the difference is between a neural net and a nonlinear transformation, right? How is it different from a nonlinear transformation we saw in some lectures ago? We were trying to transform to another space, which was a nonlinear transformation, and then, right, such as a quadratic transformation we saw on a circular shape. Yeah, it was not multilayer, but in general, so if both of them are working the same way, why somebody is trying to put all the effort to make a neural net with respect to a nonlinear transformation? If you are able to classify your nonlinear data using a nonlinear transformation, why to just put all the effort to just stack them up here? Why? Why it's not possible?
Because we cannot able to find a function that can transform every single data and create a pattern. Like we did a circular check, which was create a like in the case of circle we checked it.
Right.
So yeah, it's not possible for every kind of data that we have.
I see. What was your answer? So say if I had a more sophisticated transformation in higher order than a quadratic one, was it still be able to outperform a neural net? Say we could go up to a 17th order polynomial, right? Say you have the luxury of having a nonlinear transformation in the 17th order. Would you still go for a neural net or use that nonlinear transformation? What do you think? This is sort of a philosophical question. The simple answer would be just that Yeah, you got an answer?
I think given that we have a gradient set which we get, we can set our learning rate or we get back from our neural net, but in that case we don't have, so we won't be able to learn it for a newer.
Yeah, exactly. So even if you had the luxury to go to the 100th order polynomial, you were sort of fixed and forced to be fixed on that specific order because there was no change in weights, right? Your weights would be only constant at that specific order. Whereas in neural network, we are training it. So we adjust the weights, we play around with the perceptron to increase them and adjust to any sort of data that we have, right? So it's more flexible, it's more efficient, right? We can classify any type of data with having enough number of layers and enough number of iterations for training, right? So just like your colleagues mentioned, this makes neural network much more powerful than a fixed nonlinear transformation. And also on the other side, NN structures using different paradigms to optimize using a stochastic gradient descent and backprop, which we'll learn in a few lectures. They're very efficient in learning new data, right? Otherwise, we would have been fixed with a nonlinear transformation in whatever order that it has to apply using that specific set of weight that was fixed for that nonlinear transformation. Okay? Is that clear? All right, let me just have one more example and conclude the lecture. Example 2. So, we are interested in, this is our target classification. We have such data, we have pluses and minuses, right? In blue and red, two classes. But as you see, definitely it's not a linearly separable data, right? And as you saw, as you're seeing over there, apparently we need 3 perceptrons, and we need to stack them up as L1, L2, and L3, or H1, H2, and H3, right? To classify these 6 regions. Let's call it region 1, 2, 3, or region 1, region 2, and region 3, right? So let's see how we're going to come up visually to stack 3 neural net to come up with this. All right? So my first line, my L1, I say my H1 classifies the data on top as class minus, the one below as class plus. Okay? I define my second line, L2, which is there, as to classify this as plus and this one as minus 1. And I define this L3 so that it classifies on the right side plus 1 and on the left side minus 1. Okay? Now let's see how we're going to define different regions here. So R1, if in a case that my H1 is minus 1, which is here, so the output of this is showing this side, right? And in the case that my H2 is plus 1, so my H2 here would be plus 1, which is this. And on the case my H3 is plus 1, look at your H3 and you see on the right side it represents the plus 1. So this is this, right? If I AND them, so I have this region, and this region. The AND of these 3 regions are the ones that are actually overlapping each other, right? However, I'm not interested in overlapping all of them just as they are. in order to represent my region 1 is I need to get a negation of H1, right? Because I'm trying to represent my plus here, right? This is plus, but this classifies it as minus. So the negation of minus would be plus. So this would go plus, this is already going plus on this side, and this is already going plus on this side. So that the end of this tree is going to represent my region there. This. Is it clear? So using those 3 perceptron, I was able to play around with them, negate the first one, and use the true value of the second and third, and AND them, right? So that would be a region 1. Let's see how, can anyone have any suggestion how we're going to classify the region 2 here? Yeah.
H1, H2, H3.
Yeah. Does anyone agree with that? Are you agreeing with me? So H1, H2, and negate H3. Questions? So for R2, if I go H1, which is, let me just clear this. If I go H1, H1 is here is gonna go negative, right? And this side will be positive for H1. For H2, this side would be negative. This would be positive. This side would be negative. And H3, this side would be positive. This side would be negative. But if I negate H3, it's gonna be reversing that. So ANDing them all, I'm able to classify this. So this output actually correctly classifies this. Is it clear? Okay, so now the third region that left here, I'm able to replicate the same idea, but however, if I want to classify this as positive here, I need to negate H2 because H2 on this side was classifying it negative, so I need the negative of a negative, which is positive here, right? So the output of H2 negation of H1 negation of H2 and H3 would correctly classify this region for me. All right, so now I have 3 outputs for my positive, right? So how am I gonna sum these 3 up now? So I have 3 ANDs, right, that perfectly classify each of those regions. I want to have them all at once, right? So what I need to do is like have a sum of those ANDs, right? I'm interested in all of those outputs. So I need to sum them up, right? I need this plus this and plus this. And this is actually an OR job, right? So in general, my output is going to be 1 if and only my x's are from region R1, R2, and R3, which is an OR of the ANDs. Okay? Is it clear? 3 ORs. I mean, they could be 2 ORs. 2 ORs. Because 1 and 2, and then second and third. Right? Which doors? Oh, so that would be just one output of that. Yeah. So here would be the final layer. This could be only in one activation. Yeah. So that's why Yeah. So yeah, that was a good point. That's in my next slide. I'm going to show it to you.
Which is region 1 again?
Region. So each of those blues.
Oh.
So this is R1. R2 and R3. You could have gone for the negative one as the other regions. Okay, so basically what it does here is representing a 3-layer network, right? That accepts as input your input. The first layer has 3 nodes. Instead of 2 nodes, now I have 3 nodes, excluding the bias form, because this is the output of one of my H's, right? I have 3 lines, so the output of the H1, H2, and H3 are coming to this layer. The second one is the combination of these H1s, which I was able to produce my ANDs with. And then the last one, I'm going to produce the OR and then generate the output, just like your colleague mentioned, right? So you see, I was able to visually represent a 3-layer network. Instead of 2 now, I have 3 layers, so including the inputs. I have 1 input, 1 output, and 2 layers in middle. So overall, it's going to be 4, right? To correctly classify this region. Okay? Does that make sense? If you just look at it another time, I'm sure you're going to get the idea. It's pretty easy. And yeah. Any questions for today? All right, so I'll post some sample questions. Just read those and read through the lectures. I'm sure you're going to do fine on your midterm. Okay. See you in 2 weeks.
Oh, Professor.